What if I told you that a computer could perform more calculations in a single instant than there are atoms in the entire known universe? This isn't science fiction. It's not a thought experiment from a distant future. This is the mathematical promise of quantum computing, a technology that operates on principles so counterintuitive, so fundamentally bizarre, that even Albert Einstein struggled to accept them. We live our lives in a world of definite states. A light is either on or off. A coin toss lands on either heads or tails. Our classical computers are built on this simple binary logic. But that's not how the universe truly works at its most fundamental level. Down in the strange, fuzzy realm of subatomic particles, reality is a game of probabilities. An electron doesn't just have one position, it exists in a cloud of potential locations until we measure it. They don't deal in the certainty of a flipped switch, but in the ghostly potential of a spinning coin, mid-air. Imagine that coin isn't just spinning, it is simultaneously heads and tails, and every shade in between, all at once. To understand this revolution, we have to go back to the basic building block of all information, the bit. Each bit is a simple switch, representing either a 0 or a 1. It's a binary choice, black or white, yes or no. A qubit, however, can exist at any point on the surface of that entire sphere. It can be 0, it can be 1, or it can be a complex combination of both. With just 300 qubits, a quantum computer could represent more possible values simultaneously than there are atoms in the observable universe. If superposition wasn't strange enough, quantum mechanics has another trick up its sleeve, one that Albert Einstein famously called spooky action at a distance. This phenomenon is called quantum entanglement, and it is the second pillar upon which the power of quantum computing rests. In 2017, a Chinese satellite named Mikius successfully beamed entangled photons to two separate ground stations over 1,200 kilometers apart. This spooky connection is what allows a quantum computer to scale in a way that is truly powerful. The quest to build a useful quantum computer is not happening in a quiet university lab. It is a global race, a 21st century space race with stakes that are arguably even higher. In 2019, Google claimed to have reached this milestone with its Sycamore processor. Meanwhile, nations are treating quantum computing as a matter of national security and economic destiny. Teams are working around the clock, pushing the boundaries of what is possible. For all the incredible promise of quantum computing, there is a monumental obstacle standing in the way: reality itself. Qubits are exquisitely fragile. The slightest disturbance from the outside world can cause it to collapse. This collapse is called decoherence. Most quantum computers must be kept in massive, multi-layered refrigerators called dilution refrigerators, reaching temperatures colder than deep space. Each approach is a monumental undertaking, pushing the limits of material science, cryogenics, and control electronics. One of the first and most profound impacts of a large-scale quantum computer will be on security. Nearly all of the world's secure communications are protected by public key cryptography. But in 1994, a mathematician named Peter Shor devised a quantum algorithm that could solve the factoring problem exponentially faster. Shor's algorithm could break the encryption that protects our global financial systems in a matter of hours or days, not millennia. Recognizing this threat, governments and standards bodies are in a race to develop new forms of quantum-resistant cryptography. The true promise of quantum computing lies in its ability to create. Its greatest strength is in simulating other quantum systems, revolutionizing fields like materials science and drug discovery. A quantum computer could simulate these molecular interactions with perfect fidelity, dramatically accelerating the discovery of new medicines. The potential applications are almost limitless, from understanding Alzheimer's disease to creating new materials for everything from room temperature superconductors to more efficient solar panels. A quantum computer could unlock the secret of nitrogen fixation, potentially leading to a new way to produce fertilizer and feed the world. We stand today at a remarkable inflection point in history, similar to the dawn of the classical computer age. Few could have predicted that room-sized calculators would lead to smartphones, the internet, or artificial intelligence. We are in a similar moment of nascent potential with quantum computing. The current generation of quantum devices are powerful, but imperfect. We are still searching for the quantum transistor. What will the world look like when this technology matures? It could be a world where incurable diseases are conquered, climate change is fought with quantum-designed materials. We are building a machine that operates on the very edge of reality, one that speaks the fundamental language of the cosmos. We are at the very beginning of a new technological revolution, and the world on the other side will be a very different place. The quantum age is dawning.